What did we do? Oh yeah, we finished with Landau levels. Hell yeah. But before that, that's kind of just an example of an application of, I guess, electromagnetism and gauge invariance. So I want to keep with this theme of gauge invariance and gauge theories for the rest of the class. And today I want to introduce a lattice version of a gauge theory. Actually, what I want to do is work towards a so-called Z2 lattice gauge theory, which is equivalent to Kitaev's torque code. But before that, I want to motivate things with this sort of same gauge invariance that we explored when we were looking at electromagnetism. But all of these types of theories that have some sort of local symmetry conservation law, I think can be labeled under this category of gauge theories. These are quite important in modern condensed matter physics. Theory, I'll say theory, because gauge theories underlie the theory of quantum spin liquids, say fractional excitations. Maybe I'll say deconfined. I'll explain what some of this means. And gauge theories also underlie, or they're sort of the original motivators for why we think of, I guess, non-local correlations in terms of their entanglement in quantum condensed matter theory. If I get time, I'll talk about a little bit about entanglement in many-body systems in the last lecture. Except I have no idea what I'm going to get to. That's like 2 classes away. So lattice gauge theory, let me introduce a specific example with a Hamiltonian. So the so-called compact U1 gauge theory. This follows essentially the way it was introduced by Polyakov. Polyakov, maybe, in the 70s. Polyakov's got an awesome textbook. I forget what it's called. But it goes over all this, all the details of these gauge theories. So what the compact U1 gauge theory is just a sort of lattice version of E and M, what we did in the last class. So when I discussed, the vector and the scalar potentials, and then the Lagrangian and all these things, we were talking about a continuum limit. Like we were already in the continuum. It's like we'd done some discretization and we'd done the path integral and we'd abstracted things all the way up to the Lagrangian. But when you do that procedure, you miss important things that have to do with lattice length scale physics. And that's really what makes condensed matter field theory, if you will, or condensed matter theory a lot different than sort of high energy theory, is the idea that this lattice actually matters. The lattice underlies, it's the underlying structure of a crystal or whatever, a quantum circuit or something that you're building. So for compact U1 gauge theory, let's just redefine the Hamiltonian, this Hamiltonian version of E and M, starting with a lattice, and I'll choose a cubic lattice again, so d-dimensional. And on that lattice, I want to define variables on the links. So in 2 dimensions, we just have a square. And I'm going to use 2 different variables. One will be like your vector potential A, and one will be in an electric field. So, and they have to be canonically conjugate pair. So I'll say links are bonds. They're one-dimensional units. So in 2D, we're defining variables that live on those bonds, and in 3D, you know, it's the same story. They're called the one cells. You know, this is the 0-dimensional or vertex, the 0 cell. These are the 1 cells. The plaquettes would be the 2 cells. So you're always defining these things on 1 cells. Canonically conjugate pair. And I'll call them E's and A's. So if I label these sites with, you know, A and B for the 0 cells, or the vertices, same in 3D. You have sites A and B. Then I'm just defining these fields as living on those, living on those links, and they have a direction. Okay, so I can imagine I have A and B, and I have an E field between A and B that has a direction. So that'd be EAB. And the same for A, big A. I don't know if this is site CD. I can define ACD. Okay, they have a, okay, so this is just like a vector potential. That's why I use big A. This is like an electric field. And they have a commutation relation. Okay, and that's what makes them canonically conjugate. And let's take the Hamiltonian. To be a function of those vector fields and electric fields defined on every link. So the 2 cell, the plaquette, I'll just label with P. So I'm going to sum over all those plaquettes, which have 4 links and also 4 sites. And true to sort of Polyakhov's original Hamiltonian, I'll have cosine of the curl of A, parameterized by some big K, K prime, giving me the strength of the sum over all sites, so A's and B's are sites, the divergence of the electric field from that site. I'll draw that in a minute. I better square this thing. And then plus, I'll say, I don't know, U, sum over all links. So that's my usual notation of sort of nearest neighbor bonds. And this should be the electric field. also squared. That's just sort of given. That's just the Hamiltonian for a U1 gauge theory. Question?
What is E with just the one subscript instead of the two subscripts?
Right, so this is the divergence of E. So on the lattice, it's just all B's that are nearest neighbors of A, say. So B, nearest neighbor of A. I don't know if that's good notation. E, A, B. So if you have fields diverging, yeah, so you have a site A, say in 2 dimensions, and you have all these B's that are connected to it. So this is A, I don't know, B, C, D, E. You're summing over all of those. And then you're looking at the field strength. So a diverging field might be something like this, right? Where you're keeping track, it's like AB plus AC plus AD plus AE.
What do you mean by the curl?
Right, same thing, it's a lattice curl. So this thing here. So I'll call that a field. I've defined that on a plaquette. I get subscript with P, I guess. So it's the sum of all elements in that plaquette. A, say, A plus 1. So what that means is if I have a plaquette that's, I have to label these A plus 1s, I guess. So if I call my A 1, 2, 3, 4, then I have to define either clockwise or counterclockwise direction. So let me use clockwise. Okay, so this is just some sort of notation, but this is what it means in the lattice language. So if I had a curl, if I had a finite curl for an A field, orange, it would look something like this, you know. All right, so it's like A. Okay, start here. So it's 1. 1 plus 1 is 2. Then 2 to 3, 3 to 4, and then it has to be periodic. So then like A equals 5 equals 1. Yeah, I don't know a better way to say that. Okay, so you have this sort of lattice curl. Question?
What's the motivation for that Hamiltonian? Like, I mean, it's in super.
So you'll see in some limit, it gives you basically the Hamiltonian for QED. Yeah.
Right.
Yeah. So in the continuum limit, in some limit of these parameters, it gives you the continuum theory that we've already dealt with. But yeah, so it also has other features. So it has a basically confining, it has a Coulomb phase and has a confined phase. So it's basically what we're going to talk about. So these different parameters give you different regimes of behavior that are going to kind of mirror what we see in the Z2 theories. Right? So this is just some Hamiltonian that was basically introduced by Polyakov. Of course, there's some high energy context to it. I never learned what that was. So what does it mean? So compact U1 gauge theory. Okay, we haven't talked about any of that yet. So this Hamiltonian should be periodic in the, let's see, vector potential under addition of 2 pi. So we can require that the wave function is periodic under that transformation. So the wave function depends on many things. Let me write it like this. But let's ask that it's periodic in a vector potential, like that. We don't have to require that. But this is what's going to define the compactness of the theory. So once we do this, we can constrain essentially the values that our E's and our A's take. Okay, so since we have this commutator between our vector potential and our fields, this gives us a unitary transformation. Let me call it, I guess I'll call it the angle theta, AB. Okay, just like any canonically conjugate pair, you can define a unitary once you know the commutator. So like if you did, what, I got a plus sign there, I think it's like this. So you basically expand out these exponentials. You write all the terms in the sum. You get all these like weird nested commutators. You Baker-Hausdorff it. You'll get like AB plus theta out of that. Or I think if you just take like the first order terms in the expansion and do the commutator, you'll get the same thing. It's like the dirty way of doing it. So in order for this sort of unitary to leave the wave function invariant under 2 pi, we can replace theta by 2 pi. So e to the I theta is 2 pi. Gives the constraint that the fields must be integers. So just a constraint on that, I guess it's the eigenvalues of that operator are going to be integers. So that's what defines essentially the compact theory. Compact means that your fields, your vector potential, sorry, only can have values between 0 and 2 pi. And these are integers. Okay, there's some consequences of this that are going to come out. So it's compact. The form of the unitaries are U1. Why is it a gauge theory? It's a gauge theory because, we've defined a magnetic field in the usual way. So we have some gauge freedom in how we define the vector potential A. it's a gauge symmetry, quote unquote, because it leaves the Hamiltonian invariant. Just like it left the Hamiltonian for continuum E and M invariant. So if I transform the vector potential by, remember it's defined on links. So if I transform it by a scalar field that lives on sites, like this, then that's the gauge invariant, that's the gauge symmetry that leaves, B invariant. Okay, so it's just sort of the lattice analogy of what we did before with our E and M. So that transformation is essentially generated by, the same unitary operation. All right, we already know what the unitary is. Like, just think of this like your theta, basically. So I can write it for the whole Hamiltonian. But if I look at how my electric field is defined on, say, neighboring sites, you'll see that if I define my A and B, I'm summing over all bonds on a lattice. So I'm going to be counting, say e to the AB, which will give me XA minus XB, and also e to the BA, which will give me the opposite. So I can just associate each one of those scalar fields with an element in this lattice sum and rewrite this as the divergence. So it should be A times divergence of A. Probably up to some factor of 2 or something. Write out your divergence. You have a divergence here, right? It's got 4 fields, see? You have a divergence here, it's got 4 fields. You'll see that in that sum over all bonds, you're counting this bond twice in those 2 divergences, and you'll get factors of these chi's that you can just multiply by that divergence. So the only thing this is telling you is that divergence, because it's in that somehow, that gauge, it occurs in that gauge symmetry, that it commutes with the Hamiltonian. So divergence of E. So in the E and M sense, it means that, like, charge is conserved. We haven't included any charges explicitly in this Hamiltonian. So the total charge is conserved, because that's what the divergence is, right? Okay, so I can imagine I basically have a case where I'm looking at these, these fields A and E, but I could also write sort of the the eigenvalues of the Hamiltonian in terms of, say, the charges or something like that. And that charge is defined as like an object like that somehow, right? That has a divergence, and the E fields are integers. You could call it Q if you want. It has different values depending on the divergence, depending on the values of the E links and so on. So this is just some philosophy that I've said several times in this class, that you can imagine having sort of a vacuum state, depending on what your Hamiltonian is. And you can imagine excitations out of that vacuum being associated with elementary particles. And the particles can have a dispersion, or they can have some interaction between each other. They can be bound in pairs or unbound, called confined or deconfined. So in this type of lattice gauge theory, this just sort of shows you that, describing a charged particle with sort of this configuration of divergences around a site on the lattice would lead to this type of description. So by that philosophy, the vacuum sector would be all QA equals 0. Because QA is cost you energy, right? Yeah, there's a K prime term in the Hamiltonian. All right, so when you have charges, they cost you some energy. So the vacuum sector would be all the charges are 0. And then you can imagine putting in some energy of order K prime and exciting charges out of the vacuum. And those charged states would be just as physical. They would just be some higher energy state. Okay, so that's just one sort of term in the Hamiltonian. If I can actually look at this Hamiltonian in some limit. Let me set U to 0. So when you get rid of that E squared term, you have both this thing, the divergence, and then the curl, essentially commuting with the Hamiltonian. So then when you have a Hamiltonian like this, then the ground state is just, you take those those individual terms, one on sites A and one on plaquettes P, and you just minimize the energy contribution for each one separately. So this is what gauge theories often have. It's a nice feature that gauge theories often have. So so the ground state, okay. So it means the charge is 0. And what did I call this thing? The field. On plaquette P. So you can actually see this when you, if you assume that that magnetic field is small, and you expand out the cosine. Then your cosine's like 1 minus 1/2, whatever, like field squared, b squared. Okay, so, and that minus sign, okay, I'll drop that constant 1. So the minus sign gives me a plus k. So I just have sort of a k term and a k prime term. Right, and so any number of charges or any finite magnetic field, just increase the energy of those terms. So sort of the trivial vacuum state in that limit of u goes to 0 is easy. I could also add, a small perturbative u. To make the model actually interesting. Because it's this thing that would give you fluctuations. Right? Otherwise, you'd just be locked in that completely boring ground state. Small u gives fluctuations. And this Hamiltonian.
So far you haven't said anything about the boundary conditions, right?
Right.
So everything that you said works for any set of boundary conditions?
I'm going to say yes to that.
Yes.
Depends on what every set means, but.
Yeah, periodic boundary conditions, periodic open.
Yeah, I think it's fine, yeah. You'll have sectors, you'll have topological sectors, but I'm going to talk about that in the Z2 theories. So there is some importance with boundary conditions, but we're getting to that, okay? Let's imagine you have an infinite case right now. So this Hamiltonian, okay, so this one's supposed to be the one that reminds you of the Hamiltonian for E and M. It's just b squared and e squared, because we have expanded that cosine out. And you have this charge squared term too if you have charges in the theory. So this looks like the usual. So in fact, if you did the continuum limit properly, which now is only, assuming somehow you're in this sort of limit of parameters, so the Hamiltonian looks like this, and then you have to coarse grain a bunch of that lattice physics out, or all of that lattice physics out, you'll get something that looks like, I don't even know how to write it. I guess it would be an integral. Squared. Where you would know a bunch of the long wavelength, if you will, or continuum properties of this Hamiltonian based on its analogy to the usual Hamiltonian. And so your epsilon and your mu would be related somehow to your parameters. I never did it, so I don't know exactly how they're related. But the existence of these things, they would tell you something. You would have a photon in the theory. So it'll have linear dispersion, about k equals 0, and be gapless.
So I have two questions. First one,
Yep.
you get to the continuum limit to the classical ENM or the quantized version of ENM?
So I'm thinking Euclidean. So it could be space-time.
So you're thinking in terms of
But there's a space-time path integral.
All right, and the other thing is that you never specify the dimension.
Yeah.
But ENM in the equals 4 is super special compared to any other dimension.
Yeah, so, I mean, the compact U1 gauge theory is special up to 3D too.
Okay.
So if you did a Euclidean path integral, it's 4D in that sense. So you got, yeah. So the dimension matters. This D would be D plus 1, say. So the proper, the proper like quantum theory has to be the Euclidean path integral. It's not just some classical, completely classical case. And actually, it has all sorts of consequences for the existence of these charges. I'm not going to derive this. I just want to kind of tell you some features of this, and so that we can sort of think an analogy to the gauge theory that we already developed. But I'm going to derive a lot more stuff for the Z2 theory. So one thing, like the power of taking a continuum limit, if you could, and you would get that, is that you would know a whole bunch of things from classical E&M. Like you have a photon. It has a speed. Oh, is it square root? Is it 1 over? Or is it just square root? I forget.
It's 1 over the...
1 over this? So there's a dispersing mode that has that velocity. And then again, you can relate it to these parameters in the D plus 1 dimensional path integral. Also, this is a Coulomb, so-called Coulomb phase. It means that the charges have some sort of Coulomb repulsion or attraction depending on the relative sign, right? So have at long range. That should be something like Q A Q B for 2 charges over RAB. Okay, so the usual Coulomb interaction. And again, it just comes from analogy to E&M. But there's important features of the gauge theory that don't come out of the long wavelength limit. And I think that's the lesson that we're trying to get at here. So the long wavelength limit gives you some intuition, but you also have to be careful with sort of all of these lattice length scale constraints that are on your theory. So, for example, the lattice length scale in some sense is what tells us charges exist. Right? It's the divergence there in the blue, but also there's another type of charge. Oh, that was weird. Which is a magnetic charge. And those are where B is not small. It's exactly sort of this case I illustrated here. Right? And so the fact that those exist at the lattice length scale means that there's something beyond this sort of small b limit that you really have to worry about. Right, so something like that, depending on the strength of the A's there. And they're gapped because the energy gap is proportional to K. these are called magnetic monopoles. Okay, so just like in the Coulomb theory, in the long wavelength limit, they would have a Coulomb potential. But you can see their existence from the lattice length scale. Coulomb. At large r between the plaquettes, say. And what's special about gauge theories is these charges can't be created by local operators. So a single isolated, I mean, you're used to this when you think of monopoles, maybe. A single isolated monopole can't be created or, you know, if they don't exist in nature, they have to be created by a dipole. And it's the same with the electric charges in the theory. So let me see if I can show you how this works. So let me take a configuration with no charges for my electric fields E. And let's see what we have to do to create a divergence. So let me take all the vertical links. Maybe I'll just assume E's are 1, you know, on all the links. This is some ground state of that Hamiltonian. Did I do this right? So every divergence, yeah, it's 2 in and 2 out, so it's 0. So there's no charges anywhere on this lattice. And you create a charge. I mean, you can't do too many things, but you can imagine creating a charge by flipping this field here. So now I have 3 out, 1 in. So depending on how you value those things, that could be, say, minus Q charge. But does it live in isolation? No, because this vertex here now has, what, 3 in, 1 out? So here's another charge that's created of the opposite charge. So you can remove, you know, those things from the proximity of each other by continuing to flip the fields. So if I do this one, now I have 2 in, 2 out. So what I've done is I've moved that charge from here to here. And I can flip it again. I can flip here. I can keep flipping this row. And I can basically remove that charge to infinity. But that's a non-local operation. So I've created a charge of minus Q. Another way of thinking about it is that if you have that charge of Q, it's visible out to infinity based on this field line, essentially. So the same thing occurs for magnetic charges. I forget how this one goes. Do those have a curl? No. Okay, so you can start with the same configuration of field lines for A. I think. So if you look at this plaquette, so I'm with the arrows for 2 and against the arrows for 2, right? So the curls of all these things are 0. So if I flip one of these things, then I'm against the arrows for 3 and with it for 1, right? So this will give me a B on that plaquette. And it's the opposite for the other plaquette. I don't know what you call it, minus B. So similarly, those magnetic monopoles have to be created in pairs. If you want to see an isolated monopole, there's a non-local operation that you have to do to remove this, its partner, if you will, out to 0. Or away to infinity, sorry.
One question with respect to the gap.
Yeah.
You never mentioned what type of values can A achieve, right? You say just value between 0 and 2.
Yeah.
But cosine is a continuous function of.
Yeah, so it's a bit subtle. It's actually very subtle. Because A can be anything. So A can be very small values. So you actually have to look at the full Euclidean space path integral. And this is what Polyakov did. So he showed that basically, these, because the fact that A is a continuous variable, these things proliferate in 2 plus 1, and they destroy the phase. So I was going to mention that, but we can't see that from this. Yeah, you have to do actually a real treatment of this thing. So there's a gap. There's a gap in principle, but that gap only protects the phase actually in 3 plus 1.
Okay.
So it's just it's something important, but it's something that comes out of the path integral.
How is this similar to a magnetic monopole?
Because it's just a magnetic point charge. So it comes from the curl.
So does it have divergence? Does the field have divergence here?
So what is it? It's del dot B, which is
Equal to.
It has to be non-zero, right?
Yeah. So the reason is that you're piercing the space that's like taking the plane without a hole. So essentially the curl of A, or the divergence of the curl of A is 0 everywhere except at that point.
So at this point, right?
Yeah. So that's like a typical like vector algebra equation to not hold because you have that hole in your space.
Right.
That's very confusing.
Cool. Good answer. So yeah, I mean, you can call them anything, but they definitely call them monopoles or magnetic charges. So what did I want to say about this? Okay, so these charges can basically be, they're non-local, right? Non-local operator, they can be seen infinitely far away. Oops. Okay, so their field lines are these like purple, purple lines. If you have a charge, you can see it infinitely far away via that line. Yeah, so just we obviously haven't done a full treatment of this theory, but I just kind of want to use it to motivate the Z2 theory. So let me just say one final thing about it. And that's all this question of stability, gaps, Ks, K primes, and all this type of stuff. So in order to really understand this besides sort of, I think, the qualitative features, you have to do the full Euclidean space-time path integral. So Polyakov did this in the 70s. I recommend looking at his textbook. It's pretty awesome. He revisits these arguments in some detail. You need to, I think in order to understand the stability of the U1 phase, you need to understand a little bit about relevant and irrelevant perturbations in an RG sense. So it basically turns out that in 2 spatial dimensions, in the monopole of fugacity, sort of the potential or the the desire of the system to have monopoles causes them to proliferate in the path integral and actually destroys this sort of naive ground state. It destroys this whole Coulomb phase. So there's some very, very important dimensional dependence. And this whole picture of a Coulomb phase with charges and 1 over r's and all this type of stuff is actually only valid in 3 spatial dimensions. This is called, okay, so this phase is also called the deconfined phase. Because the charges are deconfined up to this long range 1 over r Coulomb potential. So that Polakov showed that with a full 3 + 1 Euclidean path integral. So sort of the other interesting case, which is 2D, monopoles are instantons. The instantons are created, at some time, and then they can be destroyed at some other time. And their fugacity makes them appear with a finite density. So I'll just say monopoles appear with a finite density. So this destroys the Coulomb phase. It's kind of like this proliferation of minority or defect arguments that we talked about in the Peierls instability. This is called the confined phase. Turns out that the interaction between charges goes as basically their separation distance. So there's this dimensional dependence. And then there's also this limit that we were sort of talking about where u is small. So this Coulomb phase is sort of valid in that limit in 3D. Okay, which I, of course, didn't derive. But as you increase u, or you increase the interaction, or the field strength for the electric field, I guess I should call it, then you can also have a phase transition out of the Coulomb phase. What am I going to call it? K over U, maybe? K over U critical. So when K is large, that's the Coulomb phase. Or the deconfined phase. This is the confined phase. So if they have 2 charges, QA, QB, with some distance. Right, so the energy for the 2 charges is like the Coulomb energy, whereas here it's linear. So there's a phase transition in the model, even though there's no sort of symmetry breaking. There's no spontaneous symmetry breaking globally. And so this is a very kind of common feature of gauge theories. I mean, there's many things here that are happening. There's transitions, but the transitions are in sort of the, I guess, like long wavelength characteristics of fractional charges. They're fractional because, you know, an elementary excitation of the underlying field. Remember the theories in terms of E's and A's, right? So fractional charges are essentially created in pairs because of, you know, because of this idea that you need these non-local, these essential non-local operators. And then the long wavelength behavior, sort of the confinement or deconfinement, defines a phase transition that's sort of much more complicated, maybe less intuitive than what you would see if you didn't have a gauge theory, right? So that was all supposed to give you intuition for what we're going to do in the Z2 case. Actually, the Z2 case is much simpler. It's just because, you know, we talked about gauge theories. The gauge invariance is sort of defined, or we defined it through electromagnetism. And so we can define a lattice gauge theory that recovers some features of E and M, but also has all sorts of lattice length scale physics that we have to be careful with. And actually, these U1 gauge theories are important. They may occur experimentally as emergent theories. Means that Hamiltonian, well, I mean, it's like a low energy effective theory, like everything is, right? May occur, may emerge. In these compounds called quantum spin ice. Quantum spin ice is this is what Michel Gingras studies. Ask him. But these are three-dimensional materials. I think that's one. Ooh, 07. They're they're rare earths that sit on a pyrochlor lattice, which is a lattice of corner-sharing tetrahedra. Gotta share corners here. Something like that. So the rare earths sit on the corners of these tetrahedra. And you can define effective, there's interactions that are crystal field, or of crystal field origin that can make the classical components of the spins be 2 in, something like that, 2 out. So you can have divergence-free conditions built in by the crystal field. And then if you put quantum fluctuations on these things, you can get an emergent U1 gauge theory. And so these are actually phases that people are looking for experimentally. And so this low energy theory that comes out of this U1 gauge theory is sort of the excitations and all the interactions between these magnetic and electric species are dictated by that emergent Hamiltonian. By the way, if you saw a few years ago this thing like monopoles discovered, it was in basically the classical version of this, just the regular, what they call spin ice pyrochlor. And the monopole was just this thing here. It was really just this sort of local excitation in the gauge theory. But this got so much press. Like Steve Bramall won some award in England. It was like one of the top 10 science discoveries in the BBC that year. It pays to see where these things come from, if only to be skeptical. Anyway, quantum spin ice is pretty cool. It's sort of a playground for a lot of these emerging gauge theories. That's it. That's all I want to say about the U1 theory. I didn't really derive anything. It was awesome. If I didn't cancel those classes, I might have had time, but there's not enough time left. I want to talk about the Z2 theory. This is probably one you guys are more interested in. Let me define some features of it. And I'll make an explicit connection to why it's a gauge theory, how it's related to the U1 gauge theory, what's different about it, probably next class. So I want to make an Ising theory. So recall my Ising model. has a global Z2 symmetry. For gauge theory, I don't want a global symmetry. I want a local symmetry. Let's take the Ising degrees of freedom. And make a Hamiltonian that's invariant under a local, invariant under a local Z2 symmetry. Just like you had a global sort of U1 gauge, if you will, that we studied in the context of like the two scalar or the complex scalar. Remember, that still had symmetry breaking. You did that on your assignment. Has that Mexican hat potential. You know, you have the Goldstone mode and all that stuff. That was a global U1 symmetry. And in the gauge theory we just talked about, it was a local U1 symmetry. So let's have the same philosophy. Let's start with the kind of same degrees of freedom, but make sure we have a Hamiltonian that has a local Z2 symmetry. Let me again look at a cubic or a hypercubic lattice. Okay, so in 2D, I want something like that. In 3D, and what I want to do is I want to place the Ising degrees of freedom on the links, just like my E's and my A's were on the links. Okay, so that's where my like Ising spins will reside. So all of those dots are degrees of freedom. So on the one cells, the links are the bonds. Okay. This will stay. They don't shake too much. So let me define a Hamiltonian. It looks Ising-like, but has a symmetry I'm looking for. Let me just call it minus J. Sum over all plaquettes. Let's see. Then I want to have the product of all sites around a plaquette. Sites, it should be degrees of freedom. So they're on the one cells, on the bonds. Sigma IZ. That's how you know, because I'm labeling the Ising variable. So sigma 1, sigma. I don't know, what do I do? Maybe P1, P2. So if I have a plaquette, 1, 2, 3, 4. Oh, I did it wrong. God. They're on the bonds. P, 1, 2, 3, 4. Okay, so it's the sum over all plaquettes. The product of those four spins on a plaquette, and you don't have to label, there's no labeling or convention for the direction or whatever. Because unlike E and A, there's no link, there's no direction to these links. They're just simple variables, -1, +1. Okay, that's why we're using sigma, plus or minus a half, 0 or 1, Boolean, whatever. So this term, if you just look at it, this is completely classical. Okay, we'll look at a more quantum version of the gauge theory next class. But if you look at that plaquette and you just ask, how does this energy, how is it minimized on that plaquette? There's only 2 eigenvalues of this operator. And because it's a product, it's either +1 or -1. Okay. And since you have a minus sign, you want the case where it's +1. So this term energetically favors basically an even number of spins up on a plaquette. And since there's, in any dimension, there's always 4 spins associated with the plaquette. So this is true in any dimension. So if you draw these out, so let me say sigma z is 1 is a dot, and sigma z is -1 is nothing. So if I've a plaquette with either 4 or 0 dots, it's even. You have this one. How many of these? 1, 2, 3, 4 maybe. And then like this one times 2. Should be 8, right? Yeah, okay, that's 8. So besides this local constraint, the Hamiltonian doesn't care about anything else. So the ground state of this Hamiltonian, if you put this thing in a temperature, a bath, a heat bath, and you cooled it down, the only thing that it would care about is that every plaquette is one of these 8 plaquettes, or one of these 8 spin configurations. So what results from this is an extensive ground state degeneracy, which is another hallmark of a gauge theory. So we can calculate a Pauling-like estimate for this degeneracy. The term Pauling comes from Pauling, who used this type of estimate to calculate the configurational entropy of water ice. So if you have water, if you have a lattice of ice, a lattice of water, which is called ice, then it's H2O, so every oxygen has 2 covalently bonded hydrogens, so 2 protons close, and then it has 2 hydrogen bonded, so it's hydrogen bonded to another proton that's orbiting another oxygen in 2 cases, so there's 2 farther away configurations, and whether or not you have, you know, all these protons that are in this lattice, they basically can occur either as this covalent bond or this hydrogen bond, and there's like a multitude of configurations that obey that. So that you can so Pauling estimated that to get the residual entropy of ice, and it was measured with a specific heat, I don't know, ages ago, and it was accurate within 1%. So you can do the same type of Pauling estimate for these gauge theories. I guess I just made this up. I never measured it, so. So for every plaquette, there's two conditions on this estimate. There are 8 possible configurations. Already I wrote that. I think it's different for ice water. There's probably only 6. So every plaquette like each one of these in the lattice shares that degree of freedom with some other number of plaquettes. Actually, that depends on dimension. So the probability that, the probability that neighbor is satisfied is like 1 over, so if you have a fixed configuration, it's 1 over, I guess it's 1/2. Because, I'll show you why. So probably the neighbor, or I guess the neighboring edge is satisfied is 1/2. So why is that? It's because so say I pick one of these 8 configurations. I don't know, that one. And then I randomly pick one of those 8 configurations for this one. Only half of those 8 configurations have a spin up on this particular bond here. Right, so you'll only match those 2 accurately half the time. Half the time you'll have a mismatch. And in 3D and so on, this number of edges goes up. You know, I think there's, here you're sharing 2, in 3D you're sharing 4. 4 plaquettes share an edge, and so on. So you have to increase that probability, or decrease that probability with a number of edges. So let's just look in 2D. So the number of configurations that are possible should be, so it's 8 to the number of plaquettes, the number of 2 cells, 2-dimensional cells. So that's from condition 1. And then from condition 2, only a fraction of these will satisfy the neighbors. So we'll say 1/2 to the number of edges will be satisfied. And if you look at the lattice, for each lattice site, so the 0-dimensional site, there's 1 plaquette and 2 edges. So if n is number of sites, this should be like 8n 1/2 2n. Seems right to me. That's 1/4. 8. Okay, so that's the number, that's an estimate for the number of configurations. And of course you have to worry about the next edge and the next edge and so on.
In higher dimensions, we still are looking at 4 spins on a plane?
Yeah, so this is true in any dimension here. So in higher dimensions, of course it depends how you define the Hamiltonian, but I want this to be true in any dimension. So you have like, what am I doing with my life? So you have three, each one of these planes has, plaquettes has 4 terms.
To the end rather than 1 half to the end. But this means to the end configuration.
What is this? What am I doing here? 2 to the n.
So isn't that the number of states in the Hilbert space?
Yeah, it is the same as the number of states in the Hilbert space. No, it's not. No? Because the number of states in the Hilbert space is 2 to the number of edges. So it's 2 to the 2n.
Oh, okay.
Yeah. Weird. So there's an extensive entropy associated with this. So it's S is n log 2. Again, I'm counting with number of sites or something like that. Number of 0 cells. So whatever that estimate is, the important feature, I mean, it's not exact, number 1. Obviously, because you have to worry about all the edges and so on. I never checked, but it's probably pretty close. But the important thing is it's extensive. So S goes like n, the number of sites, or the number of degrees of freedom or whatever. So that's a hallmark of a gauge theory. Compared to the Ising model, where S is just, say, equal to log 2. Right, so your entropy per n, or your entropy per spin goes to 0 in the thermodynamic limit. Okay, so again, if you accounted for all the higher order constraints, I think you get something pretty close, but you pretty much just affect that prefactor in front of the n. And so the extensivity is sort of the hallmark of a gauge theory. So you can say, oh, well, okay, well, I have a local symmetry. This is just one example. Is there any case where I can have a broken global symmetry? I mean, the answer turns out to be no. Okay, before I say that, so. Why is this a Z2 symmetry? Let me just define a transformation that's going to leave the Hamiltonian invariant. I'll call it a gauge transformation, and maybe next time I can show you how it relates to sort of your usual intuition for a gauge transformation in the U1 theory. I'll just call it some operation. So I have some site small n. Let's do it in 3D, see if it works. So in 3D, I have degrees of freedom on all of the bonds. I don't know. So let me imagine, I haven't drawn them all, but I guess you should. But imagine that I'm not going to be able to do it in 3D. But I can define Q in 3D. So Q for that site n takes all the degrees of freedom associated with that, what do I call that, site, and flips the degrees of freedom on the links. So because they're binary, it just gives me something like this. Okay, my claim is that leaves the Hamiltonian invariant on each plaquette, but I'm too lazy to try to draw that in 3D, so let's do it in 2D. Oh, I need more than one. I don't know, so let me make any sort of random configuration that satisfies the Hamiltonian. So I have to have an even number on every plaquette. Did I do it? So there's 0, 2, 2, 2. Okay. And this is my site n in the middle. So Q of n gives me I flip everything associated with it and nothing not associated with it. That one's flipped, but this one's not flipped. Did I do that right? Yeah. I think so. So here you have 4, 2, 2, and 2. So this is still in the ground state. So it leaves the Hamiltonian invariant, or the energy invariant. And at every point in space, there's two operators, the identity operator and Q. And Q squared is equal to I. That's basically your Z2 symmetry group. So you have a local conserved symmetry in the Z2 group. So you can ask the question of if you have this symmetry, can you expect to break a global symmetry in the ground state, like spontaneously? I'll just tell you the answer. The answer is no. It's called Elitzer's theorem. That's an awesome name. A local gauge symmetry cannot be spontaneously broken. Let me say it another way. Spontaneous broken symmetry means you have an expectation value, like in the Eisen case of like the magnetization, right? Your M is non-zero. So another statement is that the expectation value of any gauge non-invariant local observable can't be 0. But must be 0. And the magnetization is locally gauge invariant. So in this model, so I think you can prove this theorem for this Hamiltonian. If you if you put an external field on it, and then take the limit when the field goes to 0, although I've never done it, so I'm just guessing. But I think in general, there's definitely more general sort of proof to this that I've also never done. So the lesson is that if you want to characterize the phase in the ground state that's somehow extensively degenerate, and it's made up of all of these configurations, blah, 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 you need the expectation value of a quantity that's locally gauge invariant. Okay? And so I'll explain what that means next time, and we'll construct one of these gauge invariant quantities. It's called the Wilson loop. And we'll look at the behavior of the Wilson loop at both high and low temperatures in the Z2 gauge theory. And we'll see that there's some different qualitative behavior that again defines a phase transition, just like the confinement-deconfinement phase transition in the U1 gauge theory.
Is this theorem extended to QFT as well?
As far as I know.
But then what's the point of the left homework then? Like the Higgs mechanism is supposed to be U1 gauge broken symmetry.
But you've forced a term.
You have the gauge freedom, you choose the gauge.
Yeah, but you force a term in the Hamiltonian that explicitly breaks the symmetry. It's not just a gauge theory.
Okay.
So it's only when it's just a gauge theory. So it's just only when you have a term that's. Because if you put a term in that competes with it to break a local symmetry or the global symmetry, that counts. Yeah.
All right, and last thing, it's a little bit puzzling the fact that the entropy is extensive. Like everything we've done is at 0 temperature. Mm-hmm. So isn't this like
violating the third law of thermodynamics? I guess you worry about that sort of stuff. Yeah.
I mean, when people like keep going with this, when you find these kind of things, like I mean, if I find this and predict with that, then.
Well, the third law of thermodynamics is, I guess, meant to be broken. It just states that, I think in this case it states that if you had any perturbation on this Hamiltonian, like anything real, then you would, you would break. This is a very highly symmetric case, right?
Okay, so the caveat is the word reality. Reality,
yeah. It's definitely reality. So actually this occurs in real materials. Again, these spin ices are like a U1 gauge theory. And not the quantum versions, the classical versions where you have like a classical rare earth, like a dysprosium or homium atom sitting on the pyrochlore lattice. So if you measure the specific heat and integrate it from infinite temperature, you get an extensive entropy. And you see that it's the same gauge theory basically that defines the Pauling entropy. But what happens is if you keep looking at lower and lower temperatures, eventually there's all these perturbations that compete with like these types of Hamiltonians. Then you get long range order and 0 entropy. So it depends what you mean by reality. It's a low energy effective theory, but at some point that theory will always become invalid due to perturbations and so on. So it doesn't bother me. All right, see you guys Thursday.